Okay, welcome everybody. This is session number 4 of the Agile MBSE Lunch and Learn series. My name is Andrew Muxon. I'm here on behalf of the Heartland chapter of INCOSE, who is your host for this particular session. The session is being sponsored by Smith & Nephew. So we can thank them for bringing us here. Just kind of an overview of the Lunch and Learn series if you haven't seen it before. Dr. Bruce Powell Douglas is supporting this series. Today we'll be talking about improving requirements with use cases. We have 4 additional Lunch and Learn presentations planned, covering model-based interface control documents, handoff from system to software, model-based testing, and aMBSE and safety analysis. This, as I kind of stated before, this presentation, this entire series is being put on by INCOSE, and so we encourage you to use the INCOSE resources that we have provided here. We have 3 sectors, 74 chapters in 35 countries, so we have quite a set of resources here. In particular, this particular series is being organized by the Great Lakes North Central region, and then here we are. The Heartland chapter is this star right here. We cover the Iowa area of the state of Iowa. Your organization may well be a part of a corporate advisory board, and if it is, we encourage you to take advantage of that to join the organization as a CAB member. So here's that list of membership. INCOSE also sponsors a number of working groups and initiatives. You can see we're trying to do a lot of good systems engineering work, many of which are related to aMBSE. So please go to incose.org to learn more about membership, learn more about the systems engineering certification, the SEP program. Please join a chapter or working group. I'm part of the Heartland chapter, so feel free to join that one. And volunteer, there's many leadership positions available, meetings and events, and you get access to many publications and other products. Again, congratulations to Christopher Stopps from Cambridge, Ontario. He was the session 3 winner of Agile Model-Based Systems Engineering Cookbook. At the end of the presentation, but prior to the Q&A, we will announce an additional winner of that door prize. It's randomly drawn, but you need to be present to win. And with that, I'll introduce Dr. Douglas. He has a deep and broad experience of over 40 years, specializing in both model-based systems engineering and model-driven development for embedded software for safety critical systems. And with that, I will pass it over to him to talk about improving requirements with use cases.
Thank you. Let me share my screen. It actually worked. Okay, so welcome everybody to this 4th installment. In this section, I'm going to be talking about our session. I'll be talking about how to do use case analysis for the purpose of improving the requirements quality. That's the primary reason why you do it. There are some other benefits. We'll mention those briefly. The primary reason you do use case analysis is to come up with a complete, correct, good set of requirements. Here we go. Okay, so this slide comes from some work I did at a defense company some years ago, where they had done an analysis of the cost of poor requirements, missing requirements, requirements that are wrong, ambiguous, incomplete, inconsistent. If they identify during this more traditional lifecycle requirements specification phase, it costs about $30. If it was handed off to downstream engineers, it costs about $10,000 to fix. If it was identified as a customer, side by flying the aircraft or doing whatever they're doing, it costs $1 million plus to fix. So requirements defects have a significant impact on cost for development and maintenance of the system. And they're a kind of problem that is really expensive, but it can be mitigated if you identify the problems early. So what do we mean by good requirements? Well, we mean a number of things. That they're correct, the set of requirements is complete, it's unambiguous, that has only be interpreted one way. It's clear, which is not quite the same thing. Should be achievable, verifiable, necessary, should meet the need, should be implementation and design free, and generally speaking, it should be atomic, specify one aspect at a time. So how do we, as engineers, determine we have a good set of requirements? Well, if all you have is text, all you can do is look at it, right? So inspection and review is a really big way of doing that. Now, there is a new tool out from IBM called IBM Requirements Quality Analyzer, which is based on the Watson technology. It's not awesome. It's not bad, but it's a first kind of foray into applying AI to improve requirements quality. And as such, it's good. I do recommend it. It's good, but it doesn't really solve all the problems that we have with requirements. It identifies some things, violation of canonical forms and so on, but whether or not it's really congruent with physics of the situation and the technologies, that's something that the AI really can't solve at this point. So inspection is one way. Another thing you can do is you can test the requirements. Now, you can build models of the requirement, and we're going to talk about how to do that with SysML. And then you can execute, verify, test the requirement as a requirement in your models. And that's where we're going to primarily focus today. And you also have a thing called formal methods, where you cast the requirements in languages like Z or predicate logic, and then you can do mathematical assertions and proofs to demonstrate, demonstrable properties of the system. That's strong, but it requires, a pretty deep mathematical background to pull it off. And it's very kind of specific background to do. So it can be kind of problematic. But to be clear, when I talk about verifying the quality of the requirements, I'm talking about verifying the quality of the requirements and not verifying that the system complies with the requirements. So that latter thing is a good thing, and I certainly expect that you will do that, but that's actually not what we're talking about here. What I'm talking about here is, how do I come up with a good set of requirements so that I can hand them down to my architects and my designers and my implementers to create the system that meets the needs and does so well? How do I do that? Rather than, building the system and saying, does it comply with the requirements? That's an important thing, but not the subject of this particular talk. The requirements approach we're going to use here is usually you start off with the first cut set of requirements. So that's not universally true, but usually there's a first cut set of requirements when I come into a project, when I come in as a consultant to a project or an engineer on a project. There's usually a first cut set of textual statements, and they're usually, well, frankly, horrible. They're ambiguous, they're vague, they're imprecisely stated, they're inconsistent. There's lots and lots of missing things. So they're problematic. So we'll begin to model those sets of requirements organized around use cases to cluster requirements in terms of user-centered capabilities, something we talked about in the previous Lunch and Learn. And we represent those requirements using behavioral views, refinements, whether they're like sequence, activity, or state machine diagrams or viewpoints. We'll execute that model, and then we'll uncover poor requirements during that workflow. And then in parallel, we will then fix those, update the requirements, we'll add new requirements, we'll restate the requirements, we'll do whatever it takes to rectify the requirements defect. And we can do this in an agile way by doing a little bit, a small number of requirements at a time, building a model of that much, executing it, identifying any issues with those requirements so far, and elaborating the scope incrementally over time. So many people think that, oh, I'm doing an activity diagram, I'm doing a state machine, so I must be doing design. And that's really not the case. You know, these are behavioral specifications, and I can use them in a variety of different ways. I can use them to specify architectures, the design, or requirements. They're just a language in which I can express requirements, which is precise, executable, and in some cases formally provable. So when I talk about building this requirements model, I don't mean let's build a design model, although that can be done. Again, that's out of scope of this discussion. What I mean is when I have a shall statement, system shall do this, that implies behavior specifications. And I'm going to construct those behavioral specifications of what is required, not so much how it's done, but what needs to be done, and build a model of those to make sure that it does the right thing, and my expectations are set as to what the system should do in its operational context when it performs this particular capability. So the requirements model is really just a restatement of the text in a more formal language. I will go out of my way to avoid adding design and treat it like a black box. A lot of people have trouble with this. We talked a little bit about this in the previous Lunch and Learn, that at every level where you're specifying requirements, you should be specifying them in a black box. The element onto which we are casting requirements can't see inside that thing. I can see that externally, with these inputs, a miracle occurs and some output happens. I can specify what that miracle is. What I don't want to specify is exactly how it's achieved. That's design. But what needs to be done? What needs to be accomplished? What's the math transformations involved? That I can, in fact, specify in terms of the quality of service requirements, as well as the functional requirements. The Harmony Agile model-based system engineering process, which is described in these books, there's this notion for how do we do requirements analysis for use case basis. And this is that workflow. We start off with identifying our system use cases, and then we generate or update textual requirements. We might identify some data schemas that are involved, particularly across the flows across the system boundary. We have to specify what the flows are. Water flows in, well, how much water? What is the extent, the range, precision to which we know we were going to deal with it, the accuracy or compliance to that level of precision, the fidelity, the degree of detail with which we specify those things, all of those aspects need to be clarified, and that's done in our data schema. We analyze dependability, which is our safety, reliability, and security concerns, and we come up with a test plan for how we're going to verify that the system ultimately complies with the set of requirements. And over on the left-hand side, we have 4 different means identified for doing the actual analysis of the requirements around a use case basis. And you see that analysis is done in parallel with the update, generate update requirements. So as we do work in the analysis, we'll identify requirements defects, and in this parallel activity, we go in and fix them. That's where that happens. These 4 different approaches are small tweaks on the same basic idea. So they are kind of replaceable. You can use any of these, depending upon the nature of the problem and your own personal preferences and skill levels with the different approaches. And we'll talk about each one of those really briefly. The most common of these approaches is what I call a system function-based approach. This is particularly useful when the primary focus is on the system behaviors, system functions. What does the system do? When that's the primary focus, The workflow is shown here for that. First of all, we define the use case context. In SysML, that means we can create a block diagram where the use case is one of the blocks and the actors of the other blocks, and they have connections in an internal block diagram showing how they connect. And that forms the context of the execution of the use case. Then we'll identify the primary functional flows in an activity diagram. Now, these are the primary flows. This is, in this particular flow, this is typically incomplete. It's a sunny day, what I expect to happen kind of workflow, but not all the edge cases or exception cases. This kind of gets us started. From there, we can derive particular exemplars called scenarios, represented on sequence diagrams. Based on that, we can then define the interfaces between the system executing that capability and the actors, define those interfaces. Then we construct this normative state machine, and that becomes a single source of truth. The state machine represents all of the requirements around this use case or this capability for all possible scenarios, including edge cases, exception cases, misuse, all those kinds of rainy day scenarios, as well as sunny day scenarios. And then with verify and validate, we'll execute this model. And we can do what if analysis. Well, what if the pilot does this instead of that, or this happens in a different order? What happens in that case? Well, then we can do that what if analysis and say, this is what the system specifies will happen in that case. And if it's not what I want, then I need to fix my requirements. So this is a nice way to understand, evaluate, and verify that you have a good set of requirements. So the key aspects of this is the primary focus is on the system functions, a little bit less on the flows. And system engineers are the primary contributors to the system level understanding. The flow-based approach is really similar, but it's a slight difference in that the activity diagram will be fully elaborated to be the source of truth, the single source of truth. We won't build a state machine in this case. And that's because the flows are the primary focus. And they can be information flows. Here's patient record, and here's patient heartbeats and so on. They can be kind of information flows. They can be energy flows, fluid flows, mass flow, material flow. Where flows are the primary focus, this is the easiest way to represent that capability. So if I've got a system which heats water, and I've got flows like water coming in, cold water coming in, I've got information flows coming in like the set temperature, information going out, here's the measured temperature, and control information about turn on, turn off, and so on. And the output flow of the system is then hot water. That could be properly represented as an activity diagram where you've got continuous flows as well as discrete flows represented. So the primary application of this particular method of workflow is when the flows are the primary concern, not so much the system functions. It's not like we won't talk about system functions or specify them. It's just not the primary focus or concern. This is particularly true when you have continuous flows because state machines are inherently discrete and discontinuous. They're just inherently that kind of behavior. Whereas activity diagrams in SysML have been extended to include continuous flows. So a little bit more flexible in that respect. Scenario-based flows or interaction-based is a really common thing I'll use, particularly when working with non-technical stakeholders. So we'll work with the admiral who wants to talk about how the navigation of a ship will work, or talk to the physician who wants to talk about how we're going to deliver anesthesia to the patient. But they're not technical in the sense of the design technologies. They're not technical there. They may be deep experts in their own subject matter, and that's why we call them subject matter experts. But they're not necessarily, experts in the implementation technologies. So I can use scenarios to capture exemplars of flow. So I start off with the sequence diagrams. In this case, I'll even skip the activity diagrams, sequence diagrams, and I use that to define my ports and interfaces, my connection point interfaces. From that, I then construct this normative state machine, which represents all possible scenarios. And then I can execute and validate and verify my requirements correctness. And I can do this again incrementally as we did before. And the last of these is state-based. In this case, we actually start with the state machine. We skip the activity diagram. We start with the state machine. Because we're skipping the activity diagram starting the state machine, this is probably the most technically difficult for most people to apply because state machines are less well understood than flowcharts. And many people use activity diagrams just as kind of flowcharts. And so they kind of intuitively get sort of how that works. The state machines are a different beast, and they progress on the basis of state machine or condition transitioning to other conditions and executing behaviors along the way. So it's a little bit harder to grok for most people. So it's a little bit technically more difficult to apply this. It's also useful when the use case is particularly modal or state-based in nature. So if you're doing a shifting system for automobile, you've got drive and park and neutral and reverse, that's fundamentally a state machine. And while you can represent state behaviors in activity diagrams, it's problematic. Now, both activity diagrams and state machines are fully constructed behaviors. And you can, in principle, represent state behaviors in activity diagrams. In practice, it's kind of difficult. You have to use what are called interruptible regions in many cases. And as soon as you use interruptible regions, none of the existing tools will execute those activity diagrams. So that's a problem. And it's just easier and simpler to represent it as a state machine anyway, which will execute in tools like Cameo and Rhapsody. So state machines are a little bit harder to apply for most people. But if you're really used to state machines and comfortable with them, it's not that difficult to apply. Just most people lack that detailed understanding. Certainly, the stakeholders, the subject matter experts, will not get this. So you can't just expose the state machine to them. They won't get it. You can, however, run the state machine, generate what are called animated sequence diagrams. You can do that with Cameo, and you can also do that in Rhapsody, and then expose those to the stakeholders and say, well, in this case, pilot does this, and the ground system does that, and the other craft does this, and the navigation system does that, and these things unfold in this way. That you can expose as exemplars to the stakeholders and say, well, in this case, is that what you wanted to happen? That can be exposed, but exposing the state machine itself is problematic for most subject matter experts. Now you can see that these are all tweaks on the same basic approach. So they're alternative approaches, depending upon either the nature of the problem you're trying to solve or your preference or skill level with the technologies and system health. So some recommendations. So these are what I call Bruceisms. And that there are things that I do. It's not the only way to do it, but the things that I found effective in the, decades now that I've been using UML and SysML to model requirements and build up requirements models. So between the actors and the use case, we have messages. These are abstractions representing a flow of some kind, whether it's a control flow, sending a signal, invoking an operation or something like that, sending some sort of flow, right? So messages between actors and use cases, I will model all of them as asynchronous messages, which are signals, so signal events in SysML. Now these signals may carry data. So signals, and events can carry information, just like operation calls can. So I can send, a signal like set temperature, and I can carry the temperature I want to set the hot water heater to. So I can carry that as data if I want. So signals can carry information is the point. And so whenever you're invoking a service on the system, I model that invocation asynchronously. It technically simplifies the concurrency architecture and rendezvous concurrency semantics. It just makes things just easier to execute and flow. Later on, during the handoff, we'll refine that logical interface into whatever the actual system actually does, whether it's an electrical signal or a message sent over TCP/IP or flipping a mechanical valve, whatever it might be. But for now, if you're invoking the service, I model them as asynchronous messages or signal receptions. Messages to self, where as a part of execution of the use case, you often will invoke a service within the use case, as another system function, for example. These will be modeled either as operation calls, that is synchronous messages, or sending a signal to the same capability, an asynchronous message, right? A signal reception, depending upon whether it's synchronous or asynchronous. So system functions, I will typically model as operations and characterize as operations as part of my requirements. So what's meant by this system function is it performs this transformation, and these are the properties of the transformation. Not again how it's done, but what does it mean to perform this system function? And then you can use activities to model the methods which implement those operations for the purpose of simulation and execution. You might also send signals either to the actors, but also to the system itself for a variety of reasons. So that would be done with an asynchronous signal send. Those will be messages to self on the sequence diagram. For flows that don't involve services. So think of the hot water heater again. You have a signal that says, okay, enables, it opens up the valve, and then water flows in. So that flow, the water flow, is something that takes place over a period of time. It doesn't really invoke services per se. It's just flowing. Once you enable it, it just flows, and it goes on for some period of time. So I model that as a flow property. In my interface, I typically use proxy ports for that. So these are flow properties specified in the proxy ports. So I can talk about hot water going out or cold water coming in, electrical energy coming into the heater, so I can have heat my heating elements. Those will be flow properties. If the flow invokes a service, then I'll use asynchronous services, as I mentioned before. And as I mentioned later on the handoff, which is the last topic we'll talk about in the series, topic number 8. I think it's topic number 8. Might be topic number 7 now I think about it. We will take those and we will elaborate the actual physical interfaces. So what might be an event here might turn into a Bluetooth message in the actual implementation. That'll be my physical interface. But for now, I'm focusing on requirements, so logical interfaces are really all I need. Okay, so there's some recommendations for modeling, or actually performing the modeling of the requirements model itself. So let's look at an example. In this case, I'm going to look at a medical ventilator, and I'm going to use the scenario-based approach, which I've shown here, where we add use case context, definition. We'll identify some sequence diagrams, scenarios. From that, we'll define some interfaces between the actors and the use case or the system running the use case capability. We'll build up a normative state machine, and then we'll execute it. And then once we execute it, then we'll add our trace links to things that come before, things maybe that come after, and we can perform a review. That's the overall workflow. Medical ventilator is just shown here. Here we've got tidal volume, which is the volume per breath. We've got a breathing rate. We've got the IDE ratio, which is the inspiration to expiration ratio. We've got the positive end expiratory pressure, which is a certain amount of pressure at the end of the expiration that's maintained in the lungs to prevent alveolar collapse. It's a pretty common feature you'll have in medical ventilators. Below that, we see that there's the oxygen concentration on the inspiratory flow, partial pressure of oxygen in the blood, expired carbon dioxide, expiratory pressure, and then at the last part down here, we've got the flow rates for the various gases that are being mixed together. So that's kind of a high-level, front panel view of our patient ventilator. So here's our use case model. We've got a variety of use cases: monitor system status, monitor patient SpO2 again, that's partial pressure of oxygen in the blood. Monitor non-invasive blood pressure, mix gases, ventilate the patient, alarm, something goes wrong. The one we're going to focus on for this example is mixed gases. That's what we're going to elaborate in this example. So we start off with identifying the use case, mixed gases, and taking our first cut of requirements. In this case, there are 8 requirements here. And we build a model of this though. So I typically represent this as a separate use case diagram. I do this one per use case. What are the related requirements? I use the trace relationship. Some people use satisfy. I find that unsatisfying. I use trace. Doesn't really matter. There's a navigable relation from the use case to the requirements. And notice the direction is from the use case to the requirements. You can also represent these in tabular form, as shown here. But that's okay. So here we've got these set of 8 requirements representing what it means to mix gases. Okay, cool. Now, the first thing in the flow, once we have this use case, we're beginning the analysis, is to create the context. So in this case, I create for each one of the elements in the collaboration model, a block. This is, of course, an IBD, which shows the mixed gases connecting via these connection points, ports, to the physician, the breathing circuit, the various wall supplies, and to the tank supplies. So there's a backup tank supply if the wall supply fails for some reason, you've got a backup tank. And this central block here, mixed gases, UC mixed gases, is used to represent the capability. The reason why we use the block to represent the use case is that, one thing is blocks can have ports, and ports can be typed by interfaces. So I can be explicit about the interface definition. And that just makes it easier to do this. Also, in some tools, easier to execute behaviors associated with blocks. In Cameo, for example, I can't add ports to actors, so I'll use blocks for the actors as well in Cameo. In Rhapsody, I can actually put ports on the actors and I can use the actors directly, but fine. So I've built up this context model for the purpose of elaborating the requirements in the more formal languages I'm going to use and execution of that model. So here is a scenario sequence diagram. So here we see the lifelines. Here's the use case block here. Here's the wall supply for oxygen, breathing circuit, and the physician. And we've got a comment. I have a standard comment form that I use. Name of the use case, name of the scenario, preconditions, postconditions, describing the particular scenario. So in this case, we're going to deliver 100% oxygen. All right. And this walks through how it is. You can see that these are asynchronous messages being shown. And as we fill this out, we discover, wait a second, there are some missing requirements here. So just the act of creating the scenario means I will identify some missing requirements. The user shall select the desired gas. That wasn't in before. I need to be selecting which gas I want to set. The system shall indicate to the user what is the currently selected gas. So he's not setting the nitrogen flow when he thinks he's setting the oxygen flow. That would be bad. You want to be clear about which gas you're setting. which is the currently selected gas. Once selected, the user shall be able to set a valid flow rate. So for example, probably not negative numbers. Okay, might be able to set 0, but you can't set negative. That would be bad. User shall set the desired flow with the user action, so they can set the user action. Exactly how that's done depends on the detail of the interface. Design question, really. The system shall acknowledge the set. So not only can you set it, you get some feedback. This is what I think you told me to do. Is that right or not? If you're trying to avoid medical mishaps, right? Then we've got this loop that goes on. So every update time. So there's a requirement there about how often you want this update displayed, maybe once a second, maybe once a half second, once a minute, whatever the right time frame is. We want to see what is the measured gas flow and the measured oxygen output. Those are going to be updated every so often. So this again specifies that. And there's a requirement there. We want to have the total measured flow and measured oxygen concentration every second, plus or minus a quarter of a second. So we've got what it needs to be done and how well it needs to be done. Then we need to be able to shut the system down. There wasn't a command requirement before that said you could shut it down. You can also stop the flow. When you're at the end of the procedure, you can stop and the system acknowledges and it provides an indication that it's in fact stopped the flow. You don't want to inadvertently do this and not know that. That would be, again, potentially bad. So the act of doing this has identified some missing requirements. And in my experience of, well, a few hundred projects, this always is the case. You always identify missing or bad requirements as you walk through these processes. So notice again that the messages between the actors are shown as asynchronous signals. You can tell by the arrowhead, right? It's asynchronous. And some of these carry parameters. So the flow rate carries a parameter here because these signals can carry information as well. Another scenario. In this case, I'm going to deliver nitrogen only. So what do we expect in this case? We expect the system to say, no, you can't do that. That will kill this person. So it should reject that, right? So as we walk through this, we set the flow, we set the O2 flow to 0, and then we set the nitrogen flow to 12,000 milliliters per minute. And the system, we say, okay, enable gas flow. The system says, nope, I'm not going to let you do that. We identified a missing requirement. The system shall alert the user of the command a hypoxic mixture and then reject that command. Again, discovered missing requirements. So that was step 2. Step 3 is we want to identify the interfaces then between the system running the capability and the actors. Whenever you have associations between a use case and an actor, that implies the existence of interfaces that you probably want to specify. The sequence diagram shows them with a bit more detail. So the interface between, for example, the use case block and the physician block, here's the use case block, here's the physician, that includes service invocations, in this case, in both directions. Those should be part of those interface definitions. So I can then elaborate my IBD and show those interfaces if I want to, by showing the interface of these are the services, and you see some of them, in fact, carry parameters. Can also represent this by building up a table of that as well. So here we've got, this is the interface here. These are the signal receptions as part of the interface. And these are the parameters being passed and not shown for reasons of space, or the types and other kind of metadata that you might characterize with the, like, the flow might be within a certain range, from 0 to 20,000 milliliters per minute, with a fidelity of this and accuracy of that, and so on. Those metadata can also be captured and should be captured as part of your model. but it didn't show all of the detail here. Then we build up the formal computational model. This is that normative state machine I mentioned before in step 4. This becomes a single source of truth for the requirements in the model. Every one of these states, transitions, actions, traces back to a requirement. It's there to meet a requirement somewhere. Now, occasionally it happens that you put something in your state machine just for the purpose of facilitating execution or debugging the execution. And that's not bad, but you should indicate that those things are there not to indicate a requirement, but just to facilitate the execution. The Harmony SE toolkit, which is shipped with Rhapsody, I added to that toolkit a stereotype called non-normative. And when I do cameo modeling, I add my own Harmony toolkit profile to add non-normative, which I apply to those things. So if I have an event, send out debug information, I would tag that as non-normative, so it's clear that that is not specifying a requirement. It's just there for some other reason. If it's not otherwise specified, it indicates a requirement. And this is compliant with the standard DO 331 for use of modeling to specify avionics systems and software. So anyway, popping the stack. So here we see the states of the system, transitions, actions being performed as part of this normative state machine model. These little icon here in Rhapsody indicates, this model was done in Rhapsody, that there's a submachine, that is a nested state machine. And so I've exposed those here, bringing those out on the right-hand side. So this together represents every possible scenario for the use case mixed gases. If there's some scenario which is possible not represented, you're missing a requirement, because this completely relates the set of requirements bound to the use case with the executable model. When I execute this, I'm executing that requirements model. That's the whole kind of concept here. If I want to do what-if analysis, I can generate the system by running the simulation, inserting the events and signals and flows in a particular sequence. I can capture those on a sequence diagram. That's called an animated sequence diagram. And this is supported in both Cameo and in Rhapsody. And then I can save that for use later. And as a result of building this, identify additional requirements. So here I've identified that systems shall reject a flow that's specified as either too high or too low. So what if they try to specify 1,000,000 milliliters per minute or minus 10? They would reject that and say, I'm not going to do that. Try again. So that's what this part here does. If the flow is out of range, there's a behavior here, system function, which returns a value as a guard. And if that's true, I send an alert message out to the physician. See the sent to physician, an out of range command is rejected. And I go back to waiting for them to select a proper value. So that behavior represents how I expect the system to behave. To get ready to run the simulation, I do what I call instrumenting the actors. And that means I'm going to add non-normative behaviors to the actors to support the simulation. So I never directly manipulate, or generally speaking, never manipulate the stuff directly inside the use case during the execution. I stimulate the actors to perform the behavior. So I tell the actor, okay, you're the physician, you should set the oxygen concentration to this now, or your gas wall supply, you should start sending gas out now. So I might tell the actors to do stuff, but I want to preserve the interaction between the use case and the actors to make sure that I've understood how the system should operate in its operational context. To do that, I do what I call instrumenting the actor. So this is the state machine for the physician actor. I've added buttons here to insert events. I've got these text controls here so I can set specific values for oxygen or nitrogen or helium or air. during the execution. These are events that I will send to the actor via these buttons to select the gas flow or to set the flow or to do various things. These transitions to self here are events received back from the use case. So when it does something, it's going to say, for example, here's measured gas flow. Remember, it had to do that every second, plus or minus quarter second. Well, this is what happens to it, receives it, and it just prints out on the console. Okay, total measured gas flow is this. So that's what these things are, just receiving information from the system when it runs the capability. So that's what these parts are. And this is where sending events off to the system to perform different behaviors. Once I build this up, then I can execute different kind of scenarios to understand how the requirements work together. In my experience, well, coming up with good singular requirements is plenty hard, and certainly people fail at doing that. Coming up with a consistent, complete, correct set of requirements is much harder. And this allows me to evaluate the set of requirements and how the requirements interact during the execution of behaviors of the system. And that's immense value for complicated systems, for complex systems. So here's an example of what these simulation looks like. I captured as an animated GIF. The pink color indicates current active state. And as we insert events and run the simulation, we see the sequence diagram being drawn over on the left-hand side. That's the animated sequence diagram drawn by the tool via the execution that's going on. The green color is the last state or last transition taken. So as I run through this, I set values, I enter events, I can control the simulation and look what happens in different cases. And then I can take to my stakeholders this execution, the sequence, and say, this is what happens in this case. Does that meet your needs? Does it do what you want it to do? You can also do what if analysis. What if something happens in a different order? Here I've exposed the console output. What if, physician tries to set the flow before they start the gas? What happens in that case? Should the system reject with a message, or should just nothing happen? What should happen in that case? Well, by executing them on, you can say, well, this is what it does do now. Is that what you wanted to do? So you can do what if analysis for analysis of those requirements pretty effectively with an executable model like this. And as an output, you get these animated sequence diagrams captured here in two views. So I will run the simulations to create what I call the minimal spanning set of scenarios. That is the set of scenarios where every transition and every action is represented at least once. So you visited every place on your normative state machine. This is not only useful for understanding the flow of requirements, working with stakeholders. Later, when you want to do the create the verification plan, these form the basis for acceptance tests. So once the system is constructed, these are specifications of the test cases that will be applied to that system. In a later lunch and learn, I will be talking about model-based tests. There's a profile, the UML testing profile, that talks about kind of a standard way to do that. These can serve as the basis for the specification of those test cases. So in summary, use case analysis, as we outlined, has three primary outcomes. Improved requirements, and that's the primary reason why you do it. Identify missing requirements, that happens all the time. Incomplete or incorrect requirements, that happens a lot of the time. Make sure that requirements are explicit and ambiguous. Many requirements are, just can be interpreted by different people in different ways and are. With the state machine, what you've done in a state machine or activity diagram or sequence diagram, you're saying something really explicit and unambiguous. And then you go back to the stakeholder and say, this is what I think you meant here. do I correctly understand that? The second outcome is the logical interfaces. So we saw before, as I build up my context model and my sequence diagrams in this particular flow, I walk through those and I can cluster up the flows, whether they're asynchronous flow, which might carry information, or flow properties, and cast them as interfaces. Those are the logical interfaces that specify how the system will interact with this particular actor, well, at least for this capability. When I build my system architecture, I will merge those together from different use case analyses to form my overall interface between the system and that actor, because different use cases may have different messages involved, and typically they often do. Later on, I will refine those into physical interfaces, but depending upon the actual physical technologies being incorporated, such as communication protocols or voltage levels, or however I'm actually doing that. And the third primary outcome is this kind of first cut system verification test case specifications, those sequence diagrams. Now, that's not the final say for a couple of reasons. One is the test engineers will typically come up with more test cases as you vary values and you want to get coverage and other concerns. In addition, the ones we've created here use the logical interfaces. The test engineers will want to test the physical interfaces. So they'll have to use those as specifications for the actual test cases they want to use in the final system. There were different approaches we identified for analyzing the use cases. We talked about 4. System function-based approach, where your primary focus is on the system functions, the behaviors performed by the system when it's executing that capability, and a little bit less perhaps on the flows. This is the most common approach. And you build an activity diagram as a kind of a first cut, and you end up with this normative state machine to capture the requirements. The second was the flow-based approach, where the primary emphasis is on the flows between the actors in the system running the use case. For that, we'll use an executable activity diagram and capture the flows that way. It's very similar on system function-based though. Scenario-based is where you start with the sequence diagrams, these exemplars. It's very good for working with non-technical stakeholders to elaborate what they want in the system and use that to refine and understand the requirements. And the last one is the state-based approach, where you start with the state machine. It's technically more difficult, but it can be applicable, particularly when a system is heavily modal in nature. You can capture those states. So if you want to know more, the cookbook does have some more discussion of those different approaches in the chapter on requirements, definition, workflows, and recipes. So with that, I'd like to return control and open the floor up for questions. Please post your questions in the chat.
Right. Yes. Thank you, Dr. Douglas. Before we jump into questions, I just want to congratulate Mr. Ron Phillips, who won our random drawing for the autographed copy of Dr. Bruce's book. Mr. Phillips, if you haven't already, please reach out to Jack Stein, direct message him over the chat with your address or some contact information so we can get that book to you. Okay. Let's see, we did have a few questions in the chat. This one's from Jamie. Is there any major difference between this requirements modeling approach in Harmony and its analog in OOSEM? Is this part of the workflow seems equivalent except for some nomenclature differences?
I'd say that it's very similar. I think this is perhaps a bit more prescriptive. It gives you a bit stronger guidance. But I think they're very compatible, yeah.
Okay. We have a question from, and I apologize in advance if I butcher this name, Abel Hamid. If I stop at defining the use case scenarios and define, or better say, discover requirements there, do you think it's good enough as opposed to going on and defining the state machine diagram? I guess if you get to a certain point, is it appropriate to kind of stop and say that's good enough, or do we?
Well, of course, yeah, okay. So of course you're going to stop at some point, right? But I'm a big, huge believer in building executable models. If you just kind of do some sort of notional, something sort of kind of like that, you tend to not capture all the requirements very well. But if you build the model and then execute it, you have to be precise in your statements. And that forces you to think in more detail about precisely what's needed here. And so I really strongly recommend you build executable requirements models.
Okay. And again, a follow on to that, do you think we should always have one single state machine per use case?
That's what I do, yes. So I might have nested state machines. You saw before there were these sub-machines. But yes, there's in UML and SysML, there's this notion of a classifier behavior. So I've got a block and it has a singular classifier behavior, which is invoked when you run that. And other behaviors maybe as invoked as parts of that, but yeah, the state machine is typically the classifier behavior for that block.
All right. I myself have one question. So in this paradigm that you've presented, Dr. Douglas, you have a kind of a separation between the text-based requirements and the simulation and analysis of them. Have you seen or experienced success using, say, your behavioral diagrams, either your state machine or your activity or sequence diagrams, as the requirement itself, that is really representing what needs to happen?
If you look at DO331, it explicitly says that if you build a specification model, which is what they're talking about here, you still need to have textual requirements. However, that may not be relevant to your concern if you're not building avionics systems. In my experience, UML is not, and SysML is not consumable by all of your stakeholders. And so the textual requirements, they will want the textual requirements as a way of having human readable. Something I can read that as a physician or a pilot. I can read this and I can understand what's expected. And getting all of your stakeholders to understand SysML is a challenge. So in my experience, it's really most effective to have both. I have seen a couple of companies try to get rid of the textual requirements and only go to the model-based requirements, but they haven't been entirely successful.
Okay. I think that wraps up all the questions that we have in the chat. Thank you so much for your time, Dr. Douglas, as always. And thank you everyone for attending. Please feel free to spread the word and invite others, and please consider joining your local INCOSE chapter. Thank you. Have a good day.